Hello students, so we are going to start with the electrostatic part 2. So here it is. So till now we have talked about electric charges. Now we are going to talk about electric field. So what is electric field? The space around a charge, let a positive charge, the space around it up to which its influence can be you can say experienced by another charge is called electric field. So the definition, the space around a charge in which the electrostatic force of interaction due to the charge can be experienced by any other charge is called electric field. So, and the strength of the electric field is called electric field intensity. So the relation between electric field intensity and force. So let F be the force acting on test charge Q0. Then the electric field intensity can be given as E is equal to F upon Q0, where E is the electric field intensity. As I already told you, electric field intensity is the strength of electric field. F is the force and Q0 is the test charge, or the charge under the test, or the charge which we are observing. This is called the relation between electric field intensity, and this is very important, so mark it. So we can have a numerical on it. Say, calculate the force on an electron in an uniform field of 5 into 10 raised to power 4 Newton per Coulomb due north. Due north means the direction. So we can use this equation, that is E is equal to F upon Q0. From here what we have to find? The force. So F will be equal to E into Q0 or Q0 into E, whatever you write. So here Q0, that is the given of an electron. So what is the charge of an electron? That is 1.6 into 10 raised to minus 19 Coulomb. But it's negative always, so here direction is given, therefore we will take the negative sign. And the electric field strength is given as 5 into 10 raised to 4 Newton per Coulomb. So we can have F is equal to, put on the values, minus 1.6 into 10 raised to minus 19 into 5 into 10 raised to 4. So solve it, we will get F is equal to minus 8 into 10 raised to minus 15 Newton. As there is a negative sign, this indicates that the force of electron will be opposite to that it is due north, then this force will act towards due south. Now we have electric field intensity due to a point charge. We take a charge Q. So let it be test charge q naught placed away from it at a distance of r from it. Then we know the electrostatic force of interaction by Coulomb's law is given as F is equal to 1 by 4 pi epsilon naught. F is equal to 1 by 4 pi epsilon naught q naught upon r square. And for vector we use unit vector r. So, and beforehand we have given the relation between electric field intensity and force is F upon q naught. So put this in this, we get E is equal to 1 by 4 pi epsilon naught q upon r square. This is your electric field intensity due to a point charge. So, so if there are group of charges, for group of charges, this means our test charge will remain same, but there are many charges around. So then the electric field intensity is given as the total of all the electric field intensities, say E1, E2, E3, so on up to En. We are taking as Q1, Q2, Q3, all of their combined effects on Q naught. So electric field intensity, the overall general expression is given as 1 by 4 pi epsilon naught will remain common. We use sigma. I start from I1 till n. So Qi upon Ri square Ri unit vector. This is your electric field intensity due to group of charges. So now we will move to our next topic, that electric lines of force, or these are called field lines. We talked in 10th class about magnetic field lines. These are somewhat similar to that. So its definition can be given as, these are the path straight or curved, can be straight, can be curved, such that a tangent drawn from it gives the direction of, what are these? Electric lines. So it gives the direction of electric field at that point. Which point? From where the tangent is drawn. So these are different for different things. Like we will talk about first of all for a positive charge. Should note down that for positive charge, electric lines of forces are always outwards, and for these for positive charge, and for negative charges these are always inwards. So we have positive charge, therefore we can draw a positive charge. The electric lines of forces are always outward from the positive charge. You can draw same for the negative charge. So these are inwards, so the arrow should always be towards inwards. So we talked about positive and negative charges. Now we will talk about a dipole. What is a dipole? It is a combination of positive charge and negative charge of same intensity. So let us suppose a positive charge is placed here, negative charge is placed here. As you know, for positive lines are outwards and for negative lines are inwards. Therefore this will come as for positive, these are outward. And for negative, these are inward. This forms your electric field lines representation in dipole. If two charges are of same intensity and same charge, or similar charges, say two positive charges, say this one, say this one, say Q1, Q2, positive charge. Of course, the lines will be outwards for both, but as we know, like charges repel each other, therefore line will bend this way. You will see electric lines of forces bend towards other direction, opposite direction. Same with negative ones, but they will be in. And for a plain sheet of paper, say for a uniform charge, let it be this, containing positive charge or uniform charge, then the electric line of forces will be outward. From this side also. This completes your representation of electric field lines in positive charge, negative charge, dipole, similar charges, and uniform charge. So now important topic, that are properties of field lines or electric lines of forces. So properties. The first property is these are discontinuous curves. Discontinuous curve means that it starts from positive charge and end up in negative charge. They don't form a full whole curve. Also, there is no electric field lines inside a charged body. Electric field lines may be out just showing the charged body positive or negative by showing the outward or inward directions, but there is no electric field lines inside a charged body. Also, we know that is in definition, that tangent to it gives the direction of electric field at that point. For example, this is an electric field line. Suppose we have to find this, we will draw a tangent from here. So this is the direction of electric field. Fourth, no two field lines can intersect. This you already know why. Suppose if X is one field line and Y is another field line, they are intersecting at O. If we draw a tangent, we will find here E1, say we will find here E2. But at a single point, they not possible that there are two directions of electric field. So therefore, no two electric field lines can intersect each other. As we have seen in the dipole, the electric lines of forces contract longitudinally. So electric lines of forces contracts longitudinally. last but not the least, electric field lines are always, remember this, always normal to the surface of body. What do you mean by normal? 90 degree. See, this is a surface. Electric field lines are always normal to the surface, whether it is entering or whether it is leaving, doesn't matter, but these are always normal. So now we will move towards our next topic, that is electric dipole. So as I already told you, dipole is two polarities. So two charges separated by a small distance is called a dipole. We can say two equal and opposite charges separated by a small distance is called electric dipole. So an electric dipole consists of a pair of equal and opposite charges separated by a very small distance. So an electric dipole can be shown as, say, this is a plus q charge, this is a minus q charge. These are separated by a small distance and the distance is twice of a. This is an electric dipole. So why we taken twice of a? Because in many calculations we have to half the distance. So rather using a by 2, we will use a. So therefore it will make our calculation simple. That's why twice of a. So now dipole moment. It is just the measure of strength of electric dipole. So considering the same, we have these are equal and opposite charges. Both have same magnitude but charge is different. Dipole moment is given by small p and it is equal to q into twice of a, or this is vector form, or in magnitude we write q into twice of a, where p is the dipole moment, q is the charge, and it is the distance between these. What is the dipole field? The field around the dipole is called dipole field. Now we will move toward the very important topic of this chapter, that is field intensity on axial line of electric dipole. So what do you mean by axial line? Axial line means that line which is on the axis of that. For example, or we'll solve a question by, we'll take an electric dipole consisting of minus q and plus q charge separated by a small distance twice of a. So on the axial line, that is this line on the axis of this dipole, we take a point P where we have to find the combined effect of both of these on that point. That is the field intensity on the axial line of electric dipole. So from this, the center O, let us take the distance from here to the point P is R. Electric field intensity of this is E1 and this is E2. So E1, only we taking magnitude, will be equal to 1 upon 4 pi epsilon naught q upon AP square, this whole. distance. So this distance is, this is A, and this is R. So A plus R, AP. So 1 4 upon epsilon naught Q upon R plus A whole square, and it is along it is along PA. Why so? Because it is a negative charge. That's why the electric field will be here. Electric lines of forces is inward toward the negative. So E1 will be there along P. For E2, we will take 1 by 4 pi epsilon naught Q upon which distance? BP square. And you can, so BP you can see that is R minus A. So Q upon R minus A whole square, and it is along, for positive it is always outwards, so therefore it is along P produced. BP produced. So the net will be given as, the combined effect of both of these will be given as E is equal to E2 minus E1. Why E2 minus E1? Because the denominator here is small, so this will be large, so we will minus from a larger quantity the smaller one. Therefore we write this 1 by 4 pi epsilon naught, take it first, take it second, and both of these equations we will find Q upon R minus A whole square minus 1 upon 4 pi epsilon naught Q upon plus whole square. So combine these, Q is also common, we will take here 1 upon R minus A square minus 1 upon R plus A square. So by solving it we get R plus A square minus R minus A square upon R square minus A square whole square, or A minus B, A plus B, P minus Q, P plus Q. So combining both these we get, solve this, we get R square plus A square plus 2RA, R square plus A square minus 2RA. Cancel outs, we will get R square plus A square plus 2RA minus R square minus A square minus plus 2RA. We will get 4 pi epsilon naught, this is cancel out, we will get 4RA upon R square minus A square whole square. So now what we get, that was Q by 4 pi epsilon naught 4 AR upon R square minus A square whole square. Can we write this as 2A into twice of R upon R square minus A square whole square? And can I combine Q twice of A to R 4 pi epsilon naught? So what is this? P equal to Q to A dipole moment. Using this in this, we get E is equal to P into 2R 4 pi epsilon naught r square minus a square whole square. We get, this will be mod, we get p 4 pi epsilon naught twice of r upon, sorry, r square minus a square upon 2. This is your net electric dipole moment for the dipole on an axial line. But if dipole is very small or very short, then you can have the twice of a is very much less than r. If it is very much less than r, you can neglect a square. So we get, if we neglect a square, then 2r upon r4 or p on 4 pi epsilon naught twice r cube. As this is constant, this is constant, this is constant, this is constant, and this is constant. So we can say that if we go on increasing the distance between the dipole, the electric field strength will goes on decreasing drastically by a factor of 3. So now first we talked about axial line, now we'll talk about electric field intensity at equatorial line of electric dipole. So let me 2 points A and B having minus q charge and plus q charge separated by a small distance, say twice of A, having center O, and from center having equal distance from A and B, and from center having a distance r. So let this point be C. We have to calculate the electric field intensity by electric dipoles. So minus q here. No electric field intensity is inward for negative charge, so therefore E1 let it be here. For E2 it will go outwards, that is E2. So we will write E1 is equal to 1 by 4 pi epsilon naught q by a c square. But we don't have the distance AC. We will take in triangle AOC. AC square, it is hypotenuse we will apply PGT, is equal to base AO square plus perpendicular OC square. We will get A square plus R square, or we can write AC square is equal to R square plus A square. We'll put in this, we get E1 is equal to 1 by 4 pi epsilon naught Q upon R square plus A square. That is first equation, and it is along CA. Now E2 will be equal to 1 by 4 pi epsilon naught Q outward, where the distance is BC square. Similarly, solving this, we will have BC square is equal to R square plus A square. Put in this, we get E2 is equal to 1 by 4 pi epsilon naught Q upon R square plus A square. Mark is as equation 2. Now what we will do, we will resolve E1 and E2 both in rectangular components. As you know, for x-axis there will be cos theta and sin theta. So for E1 it will be here and here. So this will be E1 sin theta and E1 cos of theta, and E2 same. This will be E2 sin of theta, and here comes E2 cos of theta. You can see E1 sin theta and E2 sin theta, these are equal and opposite, they will cancel out each other. E2 cos theta, E1 cos theta, they are at same point from C to R, so therefore they will add up. So therefore we can write E1 sin theta and E2 sin theta will cancel out each other, whereas the total electric field will be given as E2 cos of theta plus E1 cos of theta. You can write it similarly as both are equal, so we can write 2 E1 cos of theta, as both are same, because E1 is exactly same as E2. We can write this. So put in the value, we get 2 by 4 by epsilon naught q upon r plus a square into cos of theta. So from the triangle we can find out cos theta equal to, what is cos theta? It is base upon hypotenuse. So we will get cos theta is equal to BO upon BC. So put on the value, BO is A and BC is this one here. So BC will be equal to under root of R square plus A square. So under root of R square plus A square. So put in the value of BC, we get E is equal to 2 upon 4 pi epsilon naught Q upon R square plus A square, A upon under root of R square plus A square. We can combine this as Q upon 4 pi epsilon naught upon, I can write this as, because under root is 1 by 2, so I can write 1 by 2. So just plus it out, we get, by adding we get R square plus A square 3 by 2. 3 by 2. So E will come out to be as P is equal to Q into twice of A. We get 4 pi epsilon naught 1 upon R square plus A square 3 by 2. This is the electric field intensity for an equatorial line. But if dipole is short, that is twice of A is very much less than R, therefore A square can be neglected, then it becomes, if we neglect A square, then it becomes R square 3 by 2. Multiply this, we will get 1 by R cube. Put in this, we get E is equal to P upon 4 by epsilon naught 1 upon R cube. So again, this is constant, this is constant, this is constant, this is constant. Therefore E is inversely proportional to R cube. the farther the distance of the point of observation, the less will become the electric field intensity drastically by a unit of 3. Now moving towards the next topic, that is torque on electric dipole. In many books you can read this topic as dipole in uniform two-dimensional electric field. So we will consider a uniform electric field E, and a dipole is placed at some particular angle theta, let it be minus q and this be plus q, and electric field is E, then and separated by same twice of A. Then there will be a force acting on the dipole, and for positive charge it will be in you can say direction of electric field. If it is not clearly visible, it is E. So the force acting on plus q charge will be according to here, and the force on this will be here, and electric field direction is this. So for positive it will be toward the direction of electric field, for negative it will be the opposite of the direction, electric field direction. So as we know, force on plus q is given as QE, you can say along E. And how come is this? Because we know electric field intensity is equal to force upon charge. Therefore this statement, force on minus q will be same, but only its direction will be opposite to E. So now what we will do, draw AC perpendicular to E, and first of all we will mark the points, let it be A, let it be B. Now draw AC perpendicular to this and join BC, which is parallel to electric field. We will get a right angle triangle. Therefore the perpendicular distance between the forces will be equal to this, the perpendicular distance AC, and it is also called arm of couple. So as torque is equal to force into arm of couple or the perpendicular distance, therefore tau is equal to force into AC. So what is AC? By sine theta we have perpendicular upon hypotenuse. Perpendicular is your AC, hypotenuse is your twice of A. So we will have twice of A sine of theta P, or twice of A sine of theta is equal to AC. So here we will put, get F into twice of A sine of theta, as force is equal to QE into twice of A sine of theta. So we have Q into twice of A into E sine of theta. We will get PE sine of theta. This is your torque in magnitude. So From where we get P? Because P is equal to Q into twice of A. So in vector form, it will be equal to P into cross product. Why cross product? Because sine of theta. So the direction of the tau is given by right hand screw rule and is always perpendicular to the direction of P and E, dipole moment and electric